Hi, I'm Kevin France, a professor at the University of Colorado in Boulder. Today I'm going to give you an overview of astrophysics, the big questions in astrophysics today, the tools that astrophysicists use to answer these questions, and the roles astronomers at CU Boulder play in some of this work. I'll start by giving you a few examples of big picture questions that the astrophysicists aim to answer. Then I'll focus in on what we've learned from observations with the Hubble Space Telescope, because I think Hubble serves as a great tool to understand how astronomers go about finding answers to these big questions. This also demonstrates that modern astronomy is a multi-billion-dollar enterprise that touches more aspects of modern society than you might realize. I'll go on to talk about CU's role in the Hubble Space Telescope story as one of the very few universities selected to develop and build an instrument for Hubble. I'll wrap up by talking about what I'm excited about for the future of astrophysics beyond Hubble, a new Super Hubble mission that will search for the signs of life on planets beyond our solar system. But let's start with the ground rules so we all are speaking the same language and we all know what I mean when I say astrophysics. So what is astrophysics? Well, astrophysics is the search for and the study of the laws that govern the universe. Sometimes we think of astrophysics as a little bit different than astronomy. Rather than just observation, we strive to understand the underlying physics or chemistry of an object. For instance, counting the number of red galaxies and the number of blue galaxies in this image might be astronomy. But using these images to calculate how stars form in distant galaxies, how those stars regulate the chemistry and temperature of the galaxy, and how these galaxies evolved over the age of the universe would be astrophysics. So since astrophysics is the study of the universe, it's naturally a huge even subject. But if I were to break it down into three roughly big picture questions, I think this is what I would do. I'd say 1, what is the history and fate of galaxies, black holes, and the universe? We know that galaxies and black holes developed at different times after the Big Bang, their properties have changed over time, and astrophysics aims to understand how these processes happen. 2, how do planets and stars form, and how do they change over their lifetimes? Part of the search for our origins, the history of Earth, the Sun, and our solar system, is understanding our planets, specifically our planetary system's place in the universe, and then by extension we can begin to understand how stars and planets come to be everywhere. Sometimes the best way to understand our own solar system is to look out at other solar systems forming or dying, bigger or smaller, to decipher the underlying physics that enable stars and planets to form. The third big picture question that astrophysics tries to answer is, what is Earth's place in the universe? Or, to put it another way, how does the Earth fit in with the broader family of planets? Or, really the way that I find most interesting, are we alone? Over the past 20 years, there's been a revolution in our understanding of Earth's place in the cosmos because of the discovery of thousands of planets orbiting other stars. These are the extrasolar planets, or exoplanets. Our telescopes on the ground and in space, and in particular NASA's Kepler mission, have found planets of every size and shape. As shown in this animation of all the planetary systems discovered by Kepler, to date, we've found over 3,500 exoplanets beyond the solar system, and the number will keep growing as we continue to analyze Kepler data and new missions in both the United States and Europe come online. Beyond just detecting these planets, we're now beginning to measure the properties of the planets. What are their densities? How common they are? And one of the most important questions, if we want to know if these planets could support life, do these planets have atmospheres? We are now starting to measure the pressure, the temperature, and even the composition of exoplanet atmospheres, paving the way in our search for finding planets that may support biology. Okay, so that's our brief tour of big picture astrophysics. So what do all these big picture questions have in common? Well, the observations that allowed us to make big breakthrough discoveries in these fields were all made by the Hubble Space Telescope. Why Hubble? Well, I'm going to go out on a limb and say that the Hubble Space Telescope is the most important scientific instrument in the history of humanity. It's also the most ambitious astronomy mission undertaken to date, with a total lifetime cost of almost $9 billion. So, with that introduction in mind, this next part of the presentation I want to tell you a little bit about the Hubble Space Telescope as an example of how we do astrophysics. And what I want to show you is that astrophysics is way more than some nerds sitting around in their offices thinking deep thoughts and drinking espresso and scribbling equations on a blackboard. Astrophysics is a science of action and experimentation. And I think the story of Hubble is a great example of this. So I want to start by giving you a 60-second history of Hubble before we dive into how Hubble has totally changed our understanding of the universe we live in. So this idea for a large telescope in space was first proposed by Princeton University professor Lyman Spitzer in 1948. He laid out a handful of the most pressing issues in astronomy as they were understood about 70 years ago. He described how a telescope operating above Earth's atmosphere could provide answers to these questions. Now, it took almost 25 years of lobbying his colleagues before the idea for a space telescope was championed by the National Academy of Sciences in their first decadal survey of astronomy and astrophysics, which was released in 1972. And that's really when the modern concept of the Hubble Space Telescope was born. So it took about another 18 years for NASA and its industrial partners to build the hardware and the infrastructure to support the Hubble program, including several of the key design requirements for the Space Shuttle program, which was being developed at the same time. So the Hubble project was delayed for a few years following the Challenger accident in 1986, but HST was launched aboard Shuttle Discovery in April of 1990. So here I'm showing the telescope being loaded into Shuttle Discovery's cargo bay at Kennedy Space Center in Florida, and then another image showing the deployment of the telescope on orbit. During the deployment, actually, one of Hubble's solar panels got stuck and would not deploy. The astronauts had to go out and manually tug it out. And this is really just the first part of the story that Hubble plays with manned servicing. So the astronauts saved Hubble a number of times. So one of the things that's made the Hubble Space Telescope such a long-lived observatory that continues to wow me with new images, new spectra, and new discovery has been the astronaut servicing missions. You may have heard something about Hubble's spherical aberration problem. The primary mirror in Hubble's telescope was actually ground incorrectly by the original manufacturer. Basically, Hubble was launched with an out-of-focus telescope. Nobody caught this flaw until the first images were downlinked, and they were not nearly as sharp as they were supposed to be. So the first Hubble servicing mission in 1993 retrofitted corrective optics to the instruments, essentially gave Hubble glasses that allowed the telescope to demonstrate its amazing potential and really started changing our view of the cosmos. Since then, there have been 4 other Hubble servicing missions. Each time, the space shuttle took a crew of specially trained astronauts up to fix and upgrade the observatory and outfit it with new state-of-the-art cameras and spectrographs. So what I'd like for you to take home from the backstory of Hubble is how the scientific success of Hubble would not have been possible without a strong NASA investment in the manned spaceflight, both in terms of making the Hubble servicing a priority for the Space Shuttle program, but also supporting the mission specialists and Hubble-specific training. For instance, astronaut John Grunsfeld, who later served as the Associate Administrator for NASA Science Mission Directorate, became a Hubble expert, installing new instruments on Hubble during 3 different servicing missions. So that's the backstory to Hubble, and I want to now give you an idea about how people have used HST to answer the big questions that we talked about a few minutes ago. I think we can use the Hubble story as a way to understand how scientists do astrophysics. So what does this mean, and what have we learned from Hubble? So the first thing that I want to talk about is the history of the universe. How have things changed since the Big Bang? What is our fate long into the future? To set the stage, I want to take a step back. Take a step back to our picture of the expanding universe. Basically, this is an astronomer's picture of the universe as of about the mid-20th century. We know from the pioneering work of Edwin Hubble, from whom the telescope is named, who was studying galaxies at Mount Wilson Observatory in the 20s, that galaxies are systematically moving away from us. And the farther away the galaxy is, the faster it's receding. This tells us 2 things. First, that the universe is expanding, something we refer to now as the Hubble law. And this really blew people's minds in the 1920s because at that time, the conventional wisdom was that the universe was static or fixed. So the second thing this tells us, that if we play the tape backwards and look back at very early times, asking what happened a long, long time ago, that at some point in the past, all of the galaxies had to be in the same place. This is one of the first pieces of evidence for the Big Bang, which is our picture of the universe today. But of course, we're astrophysicists, and we would like to know what's causing this expansion. Has the universe always been expanding at the same way, the same rate? Will it continue to do so in the future? Well, starting in the 80s and 90s, people set out to carefully measure the change in the expansion rate by studying distant supernovae. The idea here is that supernovae can be treated like standard candles. That is, if we can measure how bright the supernova is, we can tell how far away it is. When we combine that with measurements of how fast their host galaxies are moving away from us, or what we call the recession velocity, we can study how this Hubble law changes over cosmic time. So the trick is to find these distant supernovae, and that's where Hubble comes in. It's only Hubble's exquisite imaging resolution that allows us to clearly distinguish the bright supernovae from the surrounding galaxy. So Hubble started staring at a large number of galaxies over a long time period and eventually built up a sample of distant supernovae that we could use to measure the evolution of the universe. So The astronomers undertaking this study, and there were actually several groups from around the world chasing this question, expected to find a constant expansion rate, that the recession velocity does not change as a function of distance. Or when we look at the change of distance with velocity, in the lower plot, we expect to see this flat curve. But the results showed that the recession velocity actually changed as a function of distance. And of course, a change in velocity is an acceleration, so the supernova results show that the universe is actually accelerating. There must be some previously unknown source of pressure or energy in the universe that's pushing these galaxies apart faster at different periods in the history of the universe. So the scientists called this new mysterious energy dark energy because it did not have any known properties associated with electromagnetic radiation the way that normal matter, like stars and planets and you and me, do. So imagine this. Hubble data showed us that we were missing about 70% of all of the energy in the universe. And that was as recently as 1998. Stop and think about that. By 1998, everybody had cell phones, we had the internet, Bill Clinton was in office, and Peyton Manning was playing for the Colts. But we were missing 70% of all the energy in the universe. Normal matter, what we call baryons, the regular atomic nuclei, atoms, and molecules that make up you and me, are really only about 4 or 5% of all the energy in the universe. Whew. It really tells me how much we don't know. Maybe we're missing another 70% that your generations will be the ones to discover. So, I want to shift gears a little bit and give you 2 more quick examples of how Hubble is answering these big picture questions that we introduced at the beginning of the talk. Hubble's given us a new and incredible view into regions where the next generation of stars and planets are forming. This image is a famous example of the Eagle Nebula. Each of these large pillars is a nursery for new stars that are forming in these condensed regions of interstellar gas and dust. And inside of these star-forming regions, Hubble's been able to give us the first pictures of individual baby solar systems caught in the act of forming. These little objects are observed in the Orion Nebula, and at that distance, this is only made possible by Hubble's sharp imaging resolution. You can see the cocoon around these young planetary systems and see their disk-like shapes. This is the same shape that our solar system formed in, we think, and after about 100 million years, our disk of gas and dust dissipated, leaving the young solar system with most of the planets already in place, and Earth cooling down as it got ready to host life. Of course, finding evidence for an Earth-like or inhabited planet around another star is a search for answers to one of the oldest questions of mankind. Are we alone in the universe? Are there any other worlds where biology has begun and evolved? Are there any other worlds where that biology has turned into intelligent life? So we think the presence of an atmosphere is an essential ingredient for the development of an Earth-like biosphere. Without an atmosphere, the surface would not be protected from the harsh ultraviolet and X-rays from the parent star, precipitation cycles would not be possible, and there would be a lot less of a chance for the right soup of amino acids to come together to form the building blocks of life. So, not surprisingly, HST has also made some of the most important discoveries in the search for exoplanetary atmospheres. In 2001, Hubble made the first detection of an atmosphere on an extrasolar planet. Since then, Hubble's discovered numerous elements and molecules in exoplanetary atmospheres, including volatile elements, or those with a low boiling point, like hydrogen, oxygen, and carbon, refractory elements, or heat-resistant elements, like silicon and magnesium. They've even detected water with Hubble in the atmospheres of extrasolar planets. Now, the majority of these planets have been gas giants like Jupiter, but this work is really the first step towards characterizing the atmospheres of potentially habitable planets that we might detect in the future, and I'll return to that at the very end of the talk. I'd say that one of the most surprising findings in exoplanet science has been the presence of planets that we refer to now as hot Jupiters. These are gas giant planets that orbit very close to their parent star. After their discovery, it was theorized that because of their close proximity to their host star, these planets may be superheated, and that heat may be driving off atmospheric mass loss at extremely high rate. HST made the first detection of evaporating atmospheres from hot Jupiter, suggesting that some planets may have these long comet-like tails that are generated by extreme mass loss from their atmospheres. So we're not yet able to actually take pictures of that process, but our spectroscopic data indicates that this is actually what's happening, adding new animals to the exoplanet zoo, and capturing the imagination of both scientists and the popular media, as shown here when Jimmy Fallon highlighted some of Hubble's discovery on planets with tails. There's actually even a whole slew of online videos made by Milky J, the rapper who loves the Hubble Space Telescope, where he sings Hubble's praise on topics ranging from exoplanets to supernovae. So, To review the section on Hubble, HST has shown us that 70% of all the energy in the universe was in a form that we did not know even existed. It's provided us with some of the first pictures of baby solar systems and has proven that planets around other stars are capable of hosting rich atmospheres. So, throughout its almost 3 decades of operation, Hubble's been transforming our view of the universe, making detailed astrophysics possible, or, like Milky J says, Hubble got you. So, one of the reasons why I'm personally such a Hubble hugger is that since I've been at the University of Colorado, I've had the good fortune of being part of CU's long legacy of involvement with the Hubble Space Telescope program. So CU astronomers have been frequent users of HST since its deployment in 1990, using its cameras and spectrographs to study everything from nearby stars to young solar systems to the hot tenuous gas that pervades the material between galaxies. And one of the most famous long-term projects was carried out by CU Professor Dick McCrae with his colleagues at Harvard and Stockholm University. It's one of the only projects that Hubble has been working on for all 27 years of its life on orbit. It's about supernova 1987A. Supernova 87A is one of the nearest supernova to Earth to go off in modern times. As a result, we've had this ringside seat to its evolution over the past 3 decades. By returning to observe the supernova once or twice a year, we've been able to watch the evolution of a dying star and the dying star's interaction with its surrounding galaxy, all on human timescales. This is really unprecedented opportunity in astronomy, and it's really revolutionized our understanding of how massive stars and their lives. And again, all because of the exquisite angular resolution and spectroscopic capabilities of Hubble. But CU's Hubble story doesn't stop with making observations of our universe. So in 1997, CU astronomers were selected by NASA to build the Cosmic Origin Spectrograph, or COS. NASA announced an opportunity to build a new instrument to be installed on Hubble, an instrument that would enhance the science returned from the observatory. Astrophysical and planetary sciences professor Jim Green led a team of scientists and engineers from CU, Ball Aerospace, the NASA Goddard Space Flight Center, and the University of California to develop this new instrument for Hubble. In the next few minutes, I'll give you a quick description of the COS instrument and show you some of the path to getting COS into orbit and then onto Hubble. So, what is the Cosmic Origin Spectrograph? Well, it's an ultraviolet spectrograph. So ultraviolet means that the wavelength of light is shorter than our eyes are sensitive to. It's just beyond the blue end of the spectrum, and that light doesn't penetrate Earth's atmosphere. So if we want to see it, we've got to put our instruments into space to detect this radiation from distant objects. A spectrograph is an instrument that breaks light from your target, be it a planet or a supernova or a galaxy, into its constituent colors, and the distribution of the light and dark bands in the spectra allow astrophysicists to diagnose the composition, the temperature, and motion of the object they're looking at. Spectroscopy is an essential tool for astrophysics, and the development of spectroscopy and quantum mechanics in the early 20th century really ushered in the era of modern astrophysics as a discipline somewhat distinct from astronomy, as we discussed at the beginning of the talk. So, COS was designed to work in the ultraviolet part of the spectrum because this is where many of the strongest spectral fingerprints of important elements such as hydrogen and oxygen and carbon all reside. With ultraviolet observations, we can diagnose everything from what type of new stars are being formed in distant galaxies to how fast extrasolar planets are losing their atmospheres as they orbit their host stars. So COS was designed to be the most sensitive ultraviolet spectrograph ever flown in space. It was built and tested here at CU, at Ball Aerospace, and at Goddard Space Flight Center in the late 1990s and early 2000s. It was then launched aboard Space Shuttle Atlantis as part of Hubble Servicing Mission 4 in May of 2009. So I had the good fortune to be part of the COS team during the testing, launch, and science phases of the project, so I wanted to show a few images from how we got COS into orbit, because I think this is a really nice example of how astrophysicists get their hands dirty in some of the coolest places to work on the planet. To start, the COS instrument was shipped to Kennedy Space Center in Cape Canaveral, Florida, and installed into a mock-up of the Space Shuttle cargo bay. This image shows COS, the black phone booth-sized box, getting loaded into its shipping container for installation into the mock cargo bay and getting ready for its ride to the launch pad. Next, the mock cargo bay, with all the Hubble servicing payload on board, rolls out and takes a long, slow 2-mile drive from the processing facility to the launch pad. This staged cargo bay contains not only COS, but the other new camera that was installed on Hubble as part of the Servicing Mission 4, this is the Wide Field Camera 3, as well as replacement parts for some of the other Hubble instruments, new gyroscopes to stabilize the observatory, new flight computer, and 100 other little fixes that astronomers made during the servicing mission. All of these things were wrapped up in the test cargo bay ahead of time so everything could be fit-checked, secured, and tested, so there were no surprises when the payload gets loaded into the actual space shuttle. So to load this shuttle, the mock cargo bay is hoisted into the launch pad superstructure. This container gets pulled into the launch pad and then maneuvered into position before the left-hand side of the gantry structure swings closed. That section's actually on railroad tracks. And then the shuttle and mock cargo bay are just a few feet apart. At that point, the launch pad crew erects a temporary clean room over the shuttle cargo bay and the payload container. The payload is then transferred from the cargo container into the actual shuttle cargo bay. Picture on the left shows the inside of the Space Shuttle Atlantis just before installation started. The whole process of getting the cargo bay transferred over takes about 8 hours, and then about another 8 hours of securing the payload into the shuttle cargo bay. Picture on the right is of me in front of the Shuttle Atlantis' airlock at the end of the installation. I still can't believe that they let me in there to take part in this process, and I was very happy that COS had made it successfully into the cargo bay, and we were going to be ready to launch. The Hubble Servicing Mission 4 was launched in May of 2009 as part of Space Shuttle mission STS-125. So the COS instrument was installed on the telescope in the middle of the astronauts' 13-day stay at Hubble during Servicing Mission 4. Once the shuttle catches up with Hubble, the shuttle's Canada arm gently grabs Hubble, locks it into place in the cargo bay, and that's when the astronauts can begin their series of extravehicular activities, or EVAs. A total of 5 EVAs were performed for the maintenance of the telescope, the installation of COS and Wide Field Camera 3, and the installation of the new flight computers. All told, the astronauts spent over 36 hours doing spacewalks on Servicing Mission 4. The mission was a complete success, and Hubble became more powerful than ever. The final task for any Hubble servicing mission is to boost Hubble's orbit up about 10 nautical miles to reduce the amount of atmospheric drag on the telescope, avert an early re-entry into Earth's atmosphere, and of course, therefore, extend the working lifetime of the telescope. So, in its 7 years of operating on Hubble, COS has made discoveries that have revealed the missing matter in the intergalactic medium, measured the composition of rocky planets around nearby stars, and made the best measurements of atmospheric evaporation from hot Jupiters. It's been quite a trip to be part of the Hubble story at CU over the last decade. So, this has been my whirlwind tour of astrophysics. We looked at the big picture questions that astrophysicists work on, the tools they use, and where we hope to go in the future. We took a look at how the Hubble Space Telescope has been used to answer the most pressing scientific questions of our generation, and how CU has been a major player in both the scientific and engineering part of the Hubble story. I think CU offers so many opportunities for students to get involved with faculty and researchers working at the cutting edge of astrophysics, and really Hubble is just one piece of that. I hope that some of the work that I do today motivates you to get involved with space research and be the people that find the first signs of life on planets beyond our solar system. What?
Kevin France, Dr. Kevin France.
Yeah, who are you?
Hu Brown, PhD.
Who?
Hu Brown, PhD. I'm from the future.
The future? Well, have a seat.
Oh, that'd be great. Thank you very much.
Who?
Hu Brown. You can call me Dr. Who or Dr. Brown or Doc Brown. Doesn't matter.
All right, Dr. Who.
Thank you so much for letting me come into your office and letting me have a seat. I just finished watching your wonderful lecture on astrophysics on the YouTube video tubey thing.
Yeah, the tubes.
Yes. Anyway, in the future we call it all kinds of different stuff, but fascinating. Just total dope on that video. Great job.
Word.
But yes, I have a few questions. I was wondering if you could clarify them for me.
Sure. What do you want to know?
So basically, astrophysics and astronomy are so closely related, so similar, yet they're very different. Could you summarize once again what the fundamental differences between the two are that make them so unique?
It's a good question, Dr. Who. They are very similar, and in fact, astronomy is the foundation of astrophysics. But they're different in the level of detail which we study them. When I think about astronomy, I think about observing the visible universe. I think about understanding how many of a type of galaxy, how many planets, what there are. When I think about astrophysics, I think about really understanding the details of those objects, like what are those galaxies made of? What are those planets' atmospheres like? Can we study them in a way where we're able to understand something about, say, the surfaces of those planets? A little bit different than just astronomy.
So yeah, I think you touched on it there, visible versus in the astronomy world, what you can see. Yeah. And my next question, which is the spectrum. I know you talked and alluded to it in your your video, but could you maybe re-inform us how the spectrum plays, what the spectrum is and how it plays in the role of astrophysics?
Sure. I think the spectrum, or our field, we call it spectroscopy, is the thing that really separates astronomy from astrophysics. And so we use the spectrum. Here, I've got an example right here.
Oh,
actually.
wonderful.
Yeah,
it's like you were prepared.
Yeah, well, you know, I occasionally get visitors from the future. So we plot the spectrum in terms of its wavelength or its frequency. And so we go from long wavelengths to short wavelengths. And it's all part of one spectrum, all part of the electromagnetic spectrum. So we start with the long wavelengths, or radio waves, and then infrared light. And then as we go to the visible light that we see with our eyes, that's what I show here with this red, green, and blue color.
Rainbow.
The rainbow, that's the rainbow we see. But the spectrum keeps going. Even though our eyes don't see it, there goes into what we call the ultraviolet, and then all the way into the X-rays and gamma rays. So all of that's part of the same spectrum. And what we do in astrophysics is we use different pieces of the spectrum to understand different components of the system. And the whole spectrum allows us to do that.
And you could develop all kinds of instruments in the field of astrophysics to study, as you said, those differences that you want to discover.
That's right.
About the celestial objects. So my last question here before I release you from this interview is basically, how do you use these pieces of knowledge to better understand the cosmos at this point in history?
Right. I think we're at a very special time for spectroscopy, actually, Doctor Who.
Yes.
I feel like we're at this place right now where we're actually almost able to study life on planets around other stars. And spectroscopy is the key to all of that. We couldn't have done this 20 years ago. We didn't have the technology. Today, we have the camera systems. We have the way to block out the starlight where we can actually take a spectrum of one of these planets, just like Earth around another star, and see if there are the signs of life in its atmosphere. So it's all spectroscopy, and we're really at the right time and the right place to do it in the next couple of years.
Yeah, you're really close. You don't know how close you are, actually.
I'm beginning to wonder.
Yes.
Yeah.
Well, I really appreciate you clarifying some of these things for us in the future. And I think future viewers of your wonderful video tube are going to really enjoy these additional pieces of information.
Thanks.
So at this point, is there anything I could answer about the future for you before I leave?
Yes, I was wondering if I'm going to ever win a Nobel Prize.
Yes. You mean your first or second?
Oh, well, I'll just take my first.
Well, your first is about 20 years from now. As I alluded to, the discovery of life, or as you alluded to, you're so close, Kevin. I encourage you to keep going, because when you do discover it, the world is going to love you. But your second Nobel Prize that's coming after that is earth-shattering. I mean, it forever changes the course of history. So
that's fantastic.
I can't wait till you have
I'm
that
so
moment.
glad to hear you say that, because I was beginning to lose hope about the focus in my career. But now I know that I should keep going.
Hubble got you, man. Hubble got you.
Great.
So with that, it's time for me to show you a very special artifact from the future.
Cool.
All you need to do is you have a close look at this. Ready? Are you looking?
Yeah. Oh. I feel like I should get back to work.